My name is Matt Davis. I'm from QA Systems. I'm the Managing Director at QA Systems in the UK. Our company is headquartered in Stuttgart, and we're represented in Scandinavia by NOHAU, have been for very many years. My talk today, I had to shorten the word software because it's already a long title, Maximizing FuSa Compliant Software Test Automation. The tool I'm going to talk about mostly is Cantata. It is a certified by SGS TÜV, another one of the TÜVs, unit and integration testing tool certified to the highest safety integrity levels for all the FuSa standards. Let me start by placing testing in the software development lifecycle. Down the left-hand side of the V model, you will see system software requirements or system requirements and safety requirements, which will get embedded in system software requirements, and a decomposition of those at each level to something where you end up with code. That decomposition basically means more detail about individual items as you get them smaller. That decomposition also occurs into code. It is very common for things like system setup, defensive programming, for coders and programmers to add bits of extra detail that nobody writes down in a requirement. Okay? So just bear that little bit in mind. Verification order on the left, on the right-hand side of the V. The first thing you might do, and the reason I'm putting it up there is for sequence and order, is does your software meet a quality standard? Now, you can define that quality standard in lots of ways. The tooling involved in that is static analysis. That is what Joachim will talk about later. Static analysis should be done initially before you do dynamic testing. Why? Because if you change your code to meet a coding standard compliance or to understand or fix a perceived runtime error found by static analysis, you don't want to rework your code and your tests after you have done that analysis. So do static analysis first and then do it all again at the end. For testing, the three main things. Does the code do what it should do? Yep. Now, if you compile it, the code will do what it does. Yep. But does it do what it should do? And for that, there are basically two types of requirements. Functional requirements testing, where you specify what the function is, and hopefully in a safety or FuSa market, you are specifying a degree of functional safety requirements included in that functional requirements, and also non-functional requirements testing. So these might be performance, usability, things of that nature, timing tests. Alongside does it do what it should, does it not do what it should not do? That's a type of robustness testing. Now, don't test your software with a hammer, but that's the indication. Yeah, it's something to give you an idea. You are looking at things like all the things you possibly could find with static analysis, but in a dynamic testing environment to do so. So you may be testing things at the edge conditions, at the boundaries. You may be doing things of that nature, throwing in values that are not normally acceptable. And the third part of this is, have I tested enough? When do I stop testing with my dynamic execution? And for that, the principal mechanism is structural code coverage, measuring how much of the code constructs in your software are executed by your tests. But it is not sufficient because those lines that run black and green are requirements traceability. So it is not just has the software been tested enough, in other words, all executed, all run, but have I tested that it does all the things it should do and maybe all the things that it shouldn't do. This one area is where you will find a limit. Nobody will test their software for every possible condition, in every circumstance, forever, yeah, because you will never release anything. Okay? So there is always a trade-off between how much you do on robustness testing. But you should test all the things it should do, at least, and then hopefully all the code. Methodologies. Testing methods mirror the colors that I used on the previous slide. Static analysis is recommended by all of them, as are requirements-based testing, the various other types of testing for things like ISO 26262 for the automotive, those blue ones you can see, resource usage test and timing tests, sometimes called different things in different standards, but that's the same thing. The ones in purple are the types of robustness testing, utilizing boundary value analysis, error guessing, error seeding, error injection, these types of things. And then structural code coverage applies across all standards, but changes according to the safety integrity level. So the higher the integrity level, the more detailed the structural coverage you need to obtain. The most important fact about structural coverage is 100%. It's not getting 90% of your decisions or 90% of your statements executed. That's not enough. It is better to have 100% of a lower value metric than 90% of a higher value metric. That's why the standards require all, i.e. 100%, of the type of code constructs measured by those metrics. The hardest one to achieve is something called modified condition decision coverage. That's required by the highest safety integrity level. Does anyone in the room know what MCDC is? Don't put your hands up at the back. NOHAU, guys. Yeah? That means you're not going to have to do one of the hardest things, which is write an enormous amount of test cases to achieve it. So let's go for that. Okay. If what you are going to do is this level of testing, automation is really important. Yeah. Why? Because testing is hard work, and it takes a lot of time and effort to create the things that are necessary for functional safety certification. Automating your framework and setup configuration is what I'm going to touch on first. But before I do, I've said Cantata is a unit and integration testing tool. Most of the functional safety standards differentiate between unit testing and integration testing. So what are we talking about? Well, the Wikipedia definition is a bit rubbish, doesn't help us much. What we're actually looking at doing is executing, so verifying as a dynamic executable, running that software as a unit to check the correct internal processing and the correct uses of interfaces of that object or unit to other things. By contrast, integration testing is testing a cluster of units. Yeah? And in order to verify the cluster of units, if you are not testing at the same time, the internals, then you're looking at how those units interact. Okay? That might be about memory allocation, it might be about data being read and written to, it might be the order of calls and manipulation of things. So, if we are looking at software integration testing order, and there is potentially an overlap between unit testing and integration testing, this is an incredibly simplistic looking system. But the concept is, you can potentially start unit testing at the top, and you can then use that when you are calling other simulated objects below that you may not yet have written. The alternative is to go the other way, test from the bottom, verify those units, and use them in a test of units that call them. Both have their advantages. Another option, if you have all of the software already written, is to test it all at once. But in order to be able to test units in this, you need the controls that come where units call and interact with other units. In an integration test, you might use all of the units all the time, but you won't necessarily execute all of the code in all of the units at an integration test unless you have control to force behaviors between the units which are abnormal. This comes from a technology called wrapping. I'll come on to that in a bit. How does this work in a tool like Cantata? Basically, an integration test is like a big unit test. It's a script-driven approach. A Cantata script is written in the code language you are testing, C or C++. So with an integration test script, you build a test executable. You can have multiple units compiled together as a single exe under the control of a driver. That is your script. It's acting as the main. It allows you to simulate or intercept integrated units with your choice of script driver entry points, where you call the application, which bits you invoke, in whatever orders. Sometimes simulating and sometimes intercepting, depending on whether you have all the code. There is functionally no scalability limit. You do not have to have a really simple system like this. Yeah? You can have a million line of code application. The complexity is here. What is it all supposed to do when I'm doing something as big and as complex as that? Full Cantata unit test capabilities are available if you do an integration test like this with a script-driven approach. The alternative is not to drive your software with Cantata at all, but to use some other capabilities in Cantata. This might be an external driver. What could an external driver be? It could be something like me pressing buttons. Yeah, physically hardware, the device being activated. It could be a logic analyzer injecting data into your application. It could be all sorts of things. Where Cantata can come in this case is Cantata wrappers can be built into that application if you have source code available to test. And that gives you the interception control and invocation at whatever you want to. Those wrappers are separate from a Cantata test script. In a unit test driven by Cantata, they are integrated. And of course, code coverage of integration tests and system tests, anything that drives the software, can be measured by Cantata and combined. So if we are looking at automation, what do we need to obtain? We need a framework to drive our software. We need flexible styles of automation to execute the software. And we can determine when we re-execute the software. What do I mean by that? Regression testing. Do I test everything, every time any little bit changes? Or do I do some form of impact analysis and change-based testing? So I do a subset of my regression run every time I run a test. So firstly, with automatic test framework generation, we want to have different capabilities and styles. Am I doing unit testing? Am I doing integration testing? Am I doing black box testing where I have no knowledge of the internal of the code? Or white box testing where I do and I want that to control? Procedural C, object-oriented C++, parallel inheritance hierarchies, templates, all of these different types create different types of tests. So one tool flexible across all languages and all types. I will cover a little bit more on the powerful editing and execution and custom code injection next. And regression-wise, customizable makefiles and post-build and pre-build capabilities, as well as full Jenkins plugins and pipelines for CI/CD automation. Editing. I mentioned Cantata test scripts are written in the language you are writing, C or C++. So when you look at a Cantata test script, you can read it if you are a programmer. Yep. And if you prefer to sit there with your flickery green screen or your Vim or whatever else editor, you can do that entirely in this. Very analogous to an XUnit tool, just on steroids because it has a lot more capability than all the XUnit tools. But you also have a GUI that can do all of those things in, I would say, 99% of cases. There are some limitations around templates because it's just not possible to represent them graphically. But the structured flexible tests are independent of each other, so there is no automatic daisy chaining of test case to test case. It automatically does positive checking, i.e. what you want to check happened, and quite a lot of negative checking, so automatically initializing all accessible data to the software and checking that that data has not changed inadvertently. Yeah, so what we would call negative testing. Reusable calls between controls, and the test case generation styles allow you to choose a single function, a single method, a whole class, choose test cases as you go, test cases on objects for object-oriented type of testing, parameterized tests, so you can have the same test case with lots of different data values running through in different loops. User-defined, predefined values are available as well, and a special technology called AutoTest, which generates all the test cases for you to exercise all the code. I'll come to that in a bit more. Another capability, custom code injection. For functional safety, part of the domain here is making sure that you can exercise and inject errors and test that your software accommodates them correctly. Where you have the software and you have a test script and you are driving your software, you have control at the time that you call a function and at the time that function may call another function. After that, you're on your own. The code is the code, it does what it does. That's the whole point of the test. But sometimes you want to be able to get more fine-grained control than that. This is where custom code insertions, injections come, basically allowing you to put something before or after any individual statement, which is therefore more flexible than the call boundary for control. So it avoids conditional compilation of your code. It avoids having to use debug jumps, which are better for debugging and finding the root cause of a problem than test driving. And these are some of the example flexible use cases. Injecting errors absolutely anywhere, changing local variables under the control of the test framework, firing interrupts, breaking out of infinite loops, etc. You can even use the little text files that it generates to have changes in code. If I find a bug in the code, this is what fixes it, pass it from a tester to a developer, there you go, just write that in your code. Very useful if you have a boundary between one company and another. Some people are doing outsourced testing. So how do we generate these tests? Well, the first thing we have to do is choose what type. Set options. Which data is going to be accessed? Is it white box? Is it black box? Am I going to control, simulate, isolate functions, or am I going to intercept them? What coverage target am I going to use? Do I just want to test all the statements? I'm doing an ASIL B system in 26.2. I need to do 100% ASIL, for that 100% statement coverage. Not decision coverage, which is ASIL C, or MCDC coverage, which is all of the combinations of condition outcomes for ASIL D. So I set some options. Oh, I went a bit fast. Then what I do is, still going to go too fast. Okay, on the left-hand side, source files. We read them, we parse them. We have a built parser to Cantata. It's the world's best parser. It comes from EDG. It allows us to understand your C or C++ code. We create one file, static information file, for each source file. You select a source file to test, and Cantata with the options will generate 3 things for you if you are using AutoTest. The first thing, test scripts. Second thing, something to build the test scripts. We use basically a hierarchy of gmake makefiles in Cantata, but of course you can build them with CMake or various other build automation tools. And an AutoTest generation report if you're doing that. How we run tests is a sort of combination. You have your source code, that's the code you're testing, the called objects, which might be code that your code interfaces to, other libraries, that might be RTOS libraries from ARM, it might be Qt libraries, it might be Boost libraries, it might be anything else you build in. In the red, you have the Cantata test script, which is target independent, which means you can run the same test on multiple platforms. And a library, which is target specific, which is basically called by and used by the test script for standardized functions like check this type, start a test, end a test, report the values. And that is built for each individual architecture. The first thing we do is copy your code. We do not change your production code for testing. Okay? That's really important. A copy of your source code is instrumented. You can keep that copy if you wish to, but by default it is destroyed. And it builds an executable from all of that code. How does it do so? Under the control of the makefiles or the IDEs. You can see quite a few listed there. There are many more. When you run that test executable, you get lots of diagnostics and you get lots of reports. You can do them on the desktop. You can upload them to a server and aggregate information across the whole set of tests that you as a company are running. I mentioned configuring it for a target. This is our deployment architecture. So actually, that target library consists of a number of things: the runtime library, a deployment header file, linker commands, target BSP setup code, etc., so that we can build and create a target executable. That executable is downloaded, flashed usually from the host to the target, and when executed on the target, if you have file I/O, it generates those 3 different styles of reports: ASCII text results, graphics, and coverage. In most cases, people don't. They're not running on a full fat RTOS. They're running on a bareboard or a microkernel or whatever, in which case we use lots of different mechanisms to take the data back from the target to the host. Memory buffers can be flushed. We can use different types of connections, basically the way you would work if you are getting any analytics back from your target. And when I mean target, I don't just mean a physical board. It could be a physical board, it could be a simulator, in which case the comms is much easier, or an emulator, etc. Anything that cross-compiles. And inbuilt into Cantata is a full deployment editor to allow you to configure and set up those configurations for a target. Some platform differences can be verified by running tests on both or multiple targets. In this case, I've got my platform independent test. I'm going to pull in our host test framework, so I may be running GCC on my Windows machine or a Linux box. And I'm basically running the tests entirely on the host, getting the results locally. But I might also want to take the same tests, choose a different configuration. You can have as many configurations as you like, because you've built them in Cantata. And then you simply choose that in the IDE, run the tests, and this time the executable is flashed. Animate. The executable is flashed to the board. When that runs, you get the results here, and those are passed back over the different interfaces, which can include multiplex, demultiplex, or buffers. Yes?
Does the host test framework mean an emulator of some?
No. Basically, a host, when we consider a host, yeah, it is a host-native compilation using either GCC or Microsoft Visual Studio on a Windows or a Linux host-native machine. So if you are cross-compiling, that to us is a target. Even if you are cross-compiling to a simulator, that is still on your host machine. Yep. So in terms of building and running, yeah, sure.
So outside stimulus, like if there's a UART in play, that becomes a little bit difficult in the process.
Yes, it does, and that's why a lot of people will run tests on a target platform, even though it depends on the nature of the device, but even though they don't have to run a test on the target, and again, where you run your test is often dictated by the safety integrity level. So if you are doing an ASIL D system, or the highest level of integrity, say for a Class C device in medical, you are expected to run your test on the physical hardware. If you are doing a Class A device or an ASIL A system, you can run all your tests host native. You don't even have to use a cross-compiler. But if your application is very heavily dependent on the physical environment, it's a lot of effort to have to simulate all of the behavior of that hardware, so you might run it on the target because it's faster and more efficient to do so. And in terms of building it, we have Cantata makefiles. They're built in, as you can see, the whole lots of different types of makefiles. We have one for each of the configurations. And we also have this specialized custom.mk, and that allows you to do absolutely anything as a test is being built and run. That might mean trigger a rerun of your static analysis for that bit of software under test before you actually build and run the unit test. You could even stop the build of the run of the unit test if the static analysis fails. You might want to integrate it with your bug tracking or dashboard reporting, exporting it to Jira, firing off a ticket or something of that nature. Lots of possibilities. In terms of continuous running and building, most people adopt Jenkins. Some people do Bamboo, but it's a tiny proportion of the market. The main thing around Jenkins is the shift to pipelines. So declarative scripting is used for full pipeline automation. So you might build your software, run some static analysis, run unit tests, may be on host and on target, multiple targets. If you're parallelizing and you have a lot of tests and you want to put it across this, you might have a physical board farm of 10 different target boards. You might virtualize it all in Dockers. Lots of our customers do that. Same with integration tests. You might then trigger on to do further types of tests. And obviously you're then looking at deploy. If you are dashboarding all of this information, Jenkins provides some, but it's not brilliant. It's a minimal level of detail. We of course work with Jenkins and plug into that level, but you can then go into further types of dashboards like SonarQube or Cantata Team Reporting, which is the add-on server for aggregating results. And it's all linked, of course, from Jenkins. Basic features, it's not manual installation. Everything is deployed virtually as code on the CLI. It's very automated for DevOps and DevSecOps, and it gives you faster release cycles. And you can do it with impact analysis and change-based testing, so you don't necessarily have to run all of the things all of the time. You do a branch check-in. One more point on pipelines. You can have staged triggers. You can make them independent or dependent, and the quality gates that go past that are basically, why do I move on to the next thing? Do all of my test cases pass? If I don't get enough coverage, do I stop the pipeline, or do I go on to the next thing? That's an example of screenshot in Jenkins for the PDF records after. Automating controls is another major challenge when it comes to taking less than your whole system, because you're testing bits of it. And bits talk to other bits. And even bits in your system talk to bits outside your system, like an RTOS or a third-party code. If you are doing an isolation unit test, what you want to be able to do is to say, where I'm calling a couple of functions in my small source file with a few functions, how do I control that? Do I simulate some which is not yet written? Do I intercept some that is written but I want more control? Do I access and check and change data? Integration test, it just becomes more complex because you can extend all of that to your OS, to middle layers, to hardware, all sorts. Now, because the tests are written in C and C++, you can also embed anything you want. So where you have control, you can set and reset a hardware register or check the values of something in assembler code, inside a Cantata test. You have full flexibility. But the power of automation here is we understand what all these calls are. We understand what things are being called. We even understand the expectation that this thing should call X, Y, and Z because it can. So when it creates tests, it will create stub simulations or wrapper interceptions automatically for you with default programmable instances. So each programmable instance can do a different thing on each time a call is made. And you can have flexible call checks to check the sequence and order of these for each test case. What do I mean by simulation? Source code, called thing. Yeah, what is called thing? Anything. It could be the same object inside a source file. Function A calls function B inside source file X. It could be that called object is a third-party library. It could be Java code. It could be a database. Inside the test script, a stub is implemented. So a stub is like a dummy, a mock, a fake, if you're not familiar with the terms. All of them are simulations. They are not simulations of all the detail in here. They are just a simulation of the interface. So if I give this X and I expect Y, that's all I need to program into this. Return Y when I get X. You can check all the order of the calls, the parameters, and choose values and check values on the way out. Interception is slightly different. Interception is within the compilation unit boundary. Okay? So again, it can be done as a function with a before or after pairing of before or after replace pairing wrappers, and intercept calls specifically to calls at runtime. So in this case, Cantata automatically inserts additional functions for you to have control. The before one does everything that a simulation does, but it also allows you to change stuff. I can modify the parameters. I can see instead of this, if there is a comms problem, yeah, and actually I have corruption of data before this called object occurs, or this called object is a database and I wish to inject with an SQL injection some data specific to my test case scenario, I can do that here too. I can reset any data that is accessible to the software under test in the compilation unit boundary. But the biggest difference is this. I'm using this. I'm not simulating this. That means I can check the parameters and the returns and any values that are available to the software under test, any data that is accessible. And I can set and check post conditions and change them on the way back. So if this calls this and this is not my code, I can check my code does the right thing when this one does the wrong thing. But it's a little bit more flexible because that's the before and after. There is also the before replace pairing. That is a simulation. And you can choose which pairing you use anytime you make a call on any instance. So it's very flexible. Quick summary, advantages of that interception at integration test become more and more powerful because you cannot simulate the things you are integrating into your build. Yep, you can't have two functions declared in the same thing. The compiler will go, no. Yep. So that's how this wrapper interception works. It allows you to check rather than guess. It gives you the control you would normally get by simulating and isolating when you're doing this at integration. Data values we use to actually drive the code. The test cases we actually want to achieve. Well, test case generation from code, what we call AutoTest, is, why do we do it? To avoid too much hard work, because we're all lazy, really. No, it's not because of that. It's even in a functional safety world, developers who are writing code-based tests don't want to. Even in a functional safety, even if that's in their mindset, I only want to create safe software. I need to prove that it's safe by verification activities. The reason that they don't like doing it, because they're developers and they want to create something. Yeah? On the whole, they don't want to be testers. Now, sometimes we have companies and customers that are testers and developers at the same time in the same company. Maybe one developer tests the other developer's code. Maybe they test their own code. But it's hard work. The main reasons why it's not always easy or successful, this is the first one and probably the most important. insufficiently validated requirements to test against. Does the code do what it should do? Well, I've actually seen comment in the code, there were no requirements, this function does what it should do. Didn't say what it should do, but just that. So the reasons are non-decomposed, correct, unambiguous, logically inconsistent, and things like defensive programming and protected code. That means they end up looking at the bits of code that they haven't tested through structural code coverage and say, oh, right, I need to test that bit. I'll write a test that does that. So they end up testing the code, does what the code does, because they haven't got something that says what it should do. Complexity of test vectors. If you've got complex code and you have the combinatorial effect of many parameters affecting how a function works, it's hard work to think like this. This is what computers are for. They are very clever calculators. They can do this stuff. And efficient test case selection, whether it is boundary value analysis, choosing of data, or equivalence classing as well. So weigh up the benefits. There is an awful lot of value in automation. So how do we do it? Well, you can either choose from requirements, and test cases generated from requirements basically need good requirements. You cannot write, it does what it should do. However, the problems with natural language and even structured natural language or use case scenarios, mathematical specifications is very hard to program from those. What most people use is models. Yep, because pictures are great, say 1,000 words. The majority of the models are based off some variant of UML. Models are very good at defining requirements and generating code. But if the model that is generating the code is also generating tests for that code, it's a bit like saying it does what it does. Yeah, because the same source data is there and the same algorithm is used. So there are limitations. There is also a limitation in what a model-based testing tool can do for you. Yeah, I chaired an automotive conference a few years ago in Michigan. Most of the tier one companies there were telling us somewhere between 80 and 85% of their code base they could generate automatically in terms of tests, model-based tests. But the problem is they've got hundreds of millions of lines of code. That still leaves 15 to 20%, an enormous amount of tests that they can't test with MBT. So if you are looking at MBT and the requirements, you are able to potentially generate test cases to execute. If you are executing MBTs, then you usually can only do on a simulated host environment, not on a target environment, and there are some challenges to the thinking about how the two work together. The other option is generation from code. How can you do this? Well, somebody has already gone and implemented code that does what it should. Fingers crossed. Yep. What a tool does is it reads that code and it goes, how do I go down all these different routes? How do I exercise all of that code? How do I make sure that at this decision point, that data value is set to this, and this parameter is set to that, and that combination and combination and combination and combination are all there, so that's the route I go down. This is test vectors. So the idea is each vector is different from a previous route. Intelligent optimization is what is utilized here. The full framework needs not just to go, there's a load of stuff, it's the inputs. Do stuff, code. It should also be, what are the preconditions? How do I set this thing up? Yeah, what are the input values? Okay, that's the bashing. Expected behavior, which function should call what function? The expected outputs, in terms of function returns or data values written, etc. Postconditions. Tests also need to be generated so you can understand them. So this is not just weird machine code, but actual C or C++ code. When we do it in AutoTest, it's exactly like a Cantata test. That gives you maintainability and traceability. So the route here is generate from the code the tests. What's the major weakness in this? Does the code do what it should do? Well, only if they flipping wrote it correctly. Yeah, but that's why you're doing the test in the first place. So that is where your thinking bit comes in. Does that test verify the requirement? This is where tools really need to make sure that they are doing something that helps. So, role of driver, inject the data with the expected behaviors, help you understand the call order and enable you to control it with all these interceptions and simulations, for example. an automatic generation of all the things you need, all of the stubs, all of the interception wrappers. This is how we do it as a generation process in Cantata. We read the code, we parse it with our EDG parser, create a CSI file for each source file. We then create a node graph. We then use our test case generator to understand all of the code in that node graph, use the options. So if we want to generate test cases that execute all the functions, just call them, we can do that. If you want MCDC coverage, we can do that too, and everything in between. It also means we end up generating an abstract syntax tree of the code, correlating that to the node graph. We use an SMT path solver that we've written. We use Gaussian elimination with a test case generator so that when we are generating test cases, we understand the path and we're creating as close to an optimal set of test cases for that. So if this is really simple, those are 3 test cases, 3 routes through that code to achieve 100% decision. We want to achieve that. And if we do, the coverage analyzer built into the AutoTest approach, we end up with 3 test cases generated with a driver, a full script to execute those, along with your make files and your generation report that says, I expect to get 100% coverage. And if I don't, these are the reasons why. Very common one, unreachable code, uninitialized data values in certain places, and so on. This little example just shows the degree of optimization that we have in Cantata AutoTest. The times here are from quite a while ago, so we didn't rerun this exercise. So we're roughly about twice as fast now in terms of this. We took 55,000 lines of executable C code. We worked out with McCabe's cyclomatic complexity the number of different decision outcomes of that code. Aggregate 4,900. We created 5,035 test cases for it. That's very close to optimal. But this was a very thorough set of tests. We had 55,000 lines of executable code, and we generated 336,000, basically 6 checks for every line of code. What the hell were we checking? Everything. What the data was to start with, what the data was as it flowed through, all the call orders, all of the things that were written out. You don't have to be that thorough, but if you are, the tool will do it for you. So some use cases specifically for FuSa. The first thing you can do, run this on your code and it will tell you if it's testable. It will tell you if there's a dynamically unreachable code or crash scenarios that we will not use because you are trying to create a test that proves the code does what it does. It's not designed to make the code fall over. It's not robustness testing. You can have test cases assigned as requirements-based tests. So the test does actually tell you the right thing. You know, it's proving that the code is doing what it is supposed to do. That requires traceability. And you can have targeted test case generation. You do not have to take all your code and generate all your tests using AutoTest automatically. You can write some of your tests in Cantata, some robustness tests, some others, and go, I can't achieve 100% decision coverage. I don't know what metrics, values to use and parameters. I know, I'll choose that function and go AutoTest, and it will generate them for me, in addition to the ones you've had. So when I meant, okay, the code tests need to help you understand, is this doing what it should do? This is where the requirements stuff comes in. All of the major standards require requirements traceability, okay? Just as a highlight, this one is from DO178C, the avionics application, verifying implementation of software low-level requirements. This is 26262, complies with the unit design and fulfills the ASIL software requirements, or architectural design at integration testing, and so on. This is 62304, the medical one, a little bit more vague at this top level, yeah, but in the details, the criteria, does the software implement requirements, etc. So, how do we do tracing? How do we link? First thing to note is you link requirements to lots of things, not just to tests. You might link the requirement to the code that implements the requirement. You might link it to a contract. Yeah? So going backwards up the loop to a business need to a technical requirement. You might very commonly link a requirement for a unit design to an architectural design into which it is implemented, because that's your decomposition. What do requirements consist of? More than just an ID tag, or more than an ID tag and a single descriptor. They can include things like images, tables, hyperlinks, videos we have seen. what Cantata enables you to do is pull them all into Cantata so you can see the requirement as you are verifying and building the test. How do we do that? 3 different types: Excel, CSV, dead simple. All the best tools, RecIF, requirements interchange format, a specialized form of XML specifically for requirements. The reason RecIF is best, it's most feature-rich in terms of giving you the information. In Cantata, you see those requirements in a trace view component of the tool, and you can drag and drop them and link them with test scripts, whole scripts, for individual requirements or individual test cases, depending on the granularity you want to do. So that drag and drop assignment, so you can see here as an example, these are ones I've imported from Excel, so they're flat file format. On the right-hand side, I've got a test script, and I'm dragging that across to a requirement that applies to the whole of the code. And in this case, I have a requirement I'm going to show as an example for AutoTest linking. The requirement is a warning level too high shall be returned when the average parameters A and B are greater than 18.25. Okay, so there's a threshold there when those two averages do something, a warning level. Cantata AutoTest created a test case. The first test case it creates, it always calls default case. It's always created with nulls and zeros. It's the bottom root of the path. And then it works up from the bottom every individual test case delta vector and gives you a description. That helps you trace that test case, what it's doing to the requirement. But you can see the whole test case, not just the name of the test case or its description. So that linking is very helpful, and you can take a test case then and link it, and it'll show you within the test script. When you export it, you not only get the status of the test, pass or fail, and all of the details, you get the code coverage that's been measured with it, and all of the linked on requirements. Basically, a requirements traceability matrix is, oh yes?
Do you integrate with any of the known requirements management systems? I only know Visure, NOHAU has it in the portfolio.
Apologies, Visure doesn't fit in here yet, but I have got Visure works. Basically, Visure has a RecIF interface. Any other tools that do is really good. Yeah, there are lots of tools. The vast majority of people use Excel because it's cheap. It's not very good, but it's cheap, and everybody has it. Yeah, and you can create your pivot table, and you can have, there's your requirement, that's the bit of code that does it, that's the test case, that's the status, blah, blah, blah. Yeah?
We live in Excel, but we are considering going to Visure.
Excellent choice.
I don't know, but...
Excellent choice. We have a ton of videos that show you how it works with different tools, technical notes show you how to set it up. The one thing you do have to tell a requirements tool is what is a Cantata thing. So let me just navigate past there. Requirements traceability is needed. However, requirements also change. Yeah, unfortunately. And when requirements change, automation needs to help you too. So Cantata knows, because you have imported a set of requirements into Cantata, you can allocate them to individuals, you can have multiple requirement sets, but one of the better things is version and variant management of requirements. So my first set of requirements is like this. I've traced and linked everything. I can import another version of that requirements. I can update all the links to the new one, so basically inherit all the links I used to have, but I can also get him to show me the differences, highlight just the differences. So in this case, I've got 2 from Doors, which is a heavyweight, old school requirements management tool. And this has all the indentations and things, more detail. You can double click on each one of those and it'll open up a full HTML description with everything else in it, pictures and tables and videos, etc. But this shows me the delta. And that's very powerful because when requirements change, you don't necessarily want to go and retest everything. You know which ones have been impacted, and so you can handle a version and variant. Unfortunately, it also happens with code. People, for some reason, change code. I don't know why they do that. Surely they should write it right first time. But that doesn't happen. So when code changes, we also need to be able to automate to help you maintain your tests because they are code sensitive. They're code centric. If you have an additional parameter in a function declaration, guess what? Your test won't compile because it's not got the same declaration of the function. It'll go, right, how do I fix that? First thing, in Cantata, it compares what the last tested status of that code was with the current status of the code, and it goes, there are things that are different. It will detect them. As you can see here, these are the types of things that are detected. It will show you where they are in the code. It will then hyperlink to the code editor so you can tweak them and look at all the detail on the call stack and stuff. And it will also suggest changes automatically to refactor all of the occurrences of that change in the code. So this is helping you maintain your test. The one thing it doesn't do is go and change all your test code for you, because we might get it wrong, which is why we give suggestions. Do you want to do this one or this one or this one? In this case, it is a suggested update. My new variable static, my new static data has been added to the software under test as a static variable and should be added for use within the test script. Accept this suggestion or not. Okay, final bit. Test tool certification qualification. We work in a functional safety market. Virtually all of our customers are working in functional safety now. It used to be, all our big customers were telecoms companies. My biggest customer by a mile was Nokia. Yep, even here in Denmark. We had a whole load of companies not working in safety critical, but it would what they considered business critical environments. But certification is now the main driver, so we focus on this a lot. And we want to make this path easy. It is not just about automation. It's also about automation to achieve the certification. And this is why you're doing the testing in the first place. Not because you really like testing. You know, we all know you want to be developing. So you've got your standard. Lots of. We provide comprehensive guidance on exactly what that standard means in terms of the way you can use our tool to achieve it. Yeah? So every line, every table entry, every option in 26262 Part 6, in 62304, all of the way through, mapped into our tools. We provide advice and training with lots of technical notes and specialized training courses. And we provide certification kits and qualification kits. Anybody in here doing avionics? No, you don't have to worry about a qualification kit. For some reason, don't know why, but the RTCA D0178C standard does not allow you to pre-certify a product like a tool. You have to do it on every single project because for some reason or other, avionics costs lots of money and that's what they've decided to do. So we certify across the main functional safety standards with, as I said, SGS TÜV. We do it on every core release of Cantata. The contents of the cert kit does not just include a certification report of what they looked at. It includes a safety manual, which I'll touch on in a second, standard-specific briefing, that's all the guidance, and a results validity problem tracker, which we guarantee to tell you if anything we ever find in any of our customers will affect the validity of an outcome. That was added at the insistence of Boeing, by the way. The other thing, just to point out, is that they don't just look at our product and our processes and how we develop and maintain our software and support it. They also look at these documents. So our safety manual and standard-specific guidance is reviewed by them to say this is correct. The Qual Kit is available for avionics. You don't need to worry about it. And inside those documents, there are lots of information about use cases. So just to pick up on one, if you configure Cantata for your target architecture, you use the deployment editor, you create something called a deployment zip. You can pass that zip around and install it wherever you like. But if you don't register it with us and us tell you that it's checked and you haven't cheated, and we have had a few customers try that, basically here's the deployment, I didn't run any tests, can I use it? And we go, you can use it, but it's not certified. Yep. So if you give us the deployment, it's all free of charge to register the deployment. That's part of the process. It tells you exactly in the reports which configuration you're using, whether it's been registered, et cetera, et cetera. It's all part of the safety manual. And the safety manual covers lots of different things, tool options, control of artifacts, and so on. These are all in the PDF, so I'm not going to walk my way through them. And that's it. Accelerated functional standard compliant software testing as automated as we can possibly make it for unit and integration testing tools. That's Cantata. Any questions?